Welcome to the class. Dear students, today we are going to discuss on ionic bonds. So in this class we will see what are ionic bonds, and then we will see what is the crystal lattice structure of an ionic compound, lattice energy, and how we calculate ionic forces of attraction. Lastly, we will look into the properties, the physical and chemical properties of ionic compounds. So let us start the class. Ionic compounds. So an ionic bond is formed by transfer of electron from one atom to another. Permanent complete transfer of electron. Permanent and complete transfer of electron from one atom to another. So the atom that donates that electron, becomes positive in charge, and the atom that accepts the electron becomes negative in charge. So the positive cation that is formed by donation of electron and the anion that is formed by the acceptance of electron, these oppositely charged ions attract each other. They attract each other because opposite charges do attract each other. So these charges attract each other, and that attraction is called as the electrostatic force of attraction. This is nothing but the ionic bond or the electrovalent bond. So let us understand this better by taking an example here of NaCl. Okay, so Na has its atomic number is 11 and Cl's atomic number is 17. So I have written it like this to donate. It denotes electrons in the shells. Okay, so if I am writing the electronic configuration of sodium, you can see this is 1s2, 2s2, 2p6, 3s1. So that would be 11. 17 is the atomic number of chlorine, 287. First shell has 2 electrons, second 8, third 7. If I write the electronic configuration, that would become 1s2, 2s2, 2p6, 3s2, 3p5. So that is equal to 17 electron. Now, if you can see how many electrons are there here. How many electrons are there in the outermost shell? Outermost shell, 1 electron, right? So there is 1 electron here in the outermost shell, and here there are 7 electrons in the outermost shell. Okay, so what it does to become a stable ion, sodium does, is that it transfers this electron to this orbit of chlorine. It transfers this electron, permanent transfer of this electron to this orbit of chlorine atom, right? So now this doesn't exist, correct, when it is transferred, and here it would become 6. Now tell me the electrons in the outermost shell. This is the outermost shell of Na plus, correct, that is 8. What is the electron here in the outermost shell? 2 plus 6, 8. This is after acceptance of electron from sodium. So now after donation of electron, after donating 1 electron, it can be 2 electrons also, it can be donation of 1 or more electrons, okay, ionic bonds. So after donation of 1 electron from the 3s orbit, from the third orbit to the third orbit of the chlorine atom, sodium has attained inert configuration on the second orbit, and chlorine has attained inert configuration in the third orbit. Okay, it has attained inert configuration at the third orbit. So what I have said here, after donation of 1 electron from the third orbit, there was a third orbit here, to the third orbit of chlorine, sodium has attained inert configuration in the second orbit, and chlorine has attained inert configuration at the third orbit. So it is all to attain an inert configuration, correct? Why sodium is donating electron to chlorine? To attain inert configuration, okay, inert configuration. So now what happens? Sodium becomes positive and chlorine becomes negative. Yes, after donation it becomes positive, and after acceptance it becomes negative. Let us understand this by means of diagram. These are the electrons of the sodium you can see first shell has 2 electron, second shell has 8 electron, and the third shell has 1 electron. Here also the first shell has 2 electron, second shell has 8 electrons, and third shell has 7 electrons. What happens? This electron gets donated here, right? So from the third orbit of sodium to the third orbit of chlorine, completely transfer, permanent transfer. Now this orbit ceases to exist. There is no electron here. So now there is 8 electron in the outermost shell of sodium and 8 electrons in the outermost shell of chlorine. This becomes a positive. Why? Because actually initially before donation the atom was neutral, correct? At that situation, when the situation was like that, the number of proton was equal to number of electron. Now when that electron has gone here, what would happen? The number of proton is more than the number of electrons. So that results in positive sign here, correct? Here also initially when it was chlorine, just chlorine, okay, no acceptance has taken place. Then what was the situation? The number of proton was equal to number of electron. Now when the acceptance have taken place, when it has accepted, the number of electron became greater than number of proton by 1 charge. So here it is +1, here it is -1, charge is -1. Now what would happen is that they are very close to each other. Obviously that is why it has donated the electron. So being so close to each other, what happens? The oppositely charged ions, they start attracting each other. A force of attraction comes into play. This force of attraction is because of electric charges developed which are static, and therefore this force of attraction is called as the electrostatic force of attraction. Electrostatic force of attraction. This electrostatic force of attraction is nothing but the ionic bond. It is nothing but the ionic bond. That force of attraction is itself the ionic bond. And why do we call it ionic bond? Because this force of attraction exists between ion pairs. So that is why that force of attraction is called as ionic bond. It is also called as electrovalent bond. Electrovalent bond. Why is it called electrovalent? Because the electric charges has been developed. It was not there initially. It was developed due to transfer of valence electron from the outermost shell of one atom to the outermost shell of the other atom. So because these electric charges were developed due to the transfer of valence electron, it is also called as electrovalent electrons, electrovalent bond. So that is the introduction of ionic bond. That is the introduction of ionic bond. Now let us discuss the conditions to form ionic bond. There is only one condition to form ionic bond. See, this is sodium atom, this is chlorine atom. The two atoms involved should have significant electronegativity difference. It should have significant electronegativity difference. That electronegativity difference should be significant. Okay. Take for example, if I am replacing Na plus by H plus, okay, and Cl is the same, will there be any ionic bond here? No. Right? Will there be any ionic bond here? No. Correct? There will be no ionic bond here. But will there be ionic bond here? Yes. Correct? Will there be ionic bond here? No. Will there be ionic bond here? Yes. Why? Because there is significant electronegativity difference between sodium and bromine. Between sodium and bromine. Here in HCl, HF and HBr, we are witnessing polar covalent bond. We see polar covalent bond. Polar covalent bond. Okay. It is not ionic bond, it is polar covalent bond. There is mutual sharing of electron, but that mutual sharing of electron is not equal. It is the electron cloud is shifted towards the more electronegative atom. There is no complete transfer of electron. There is no permanent transfer of electron. It is just the shift of electron cloud towards the more electronegative atom. So that is what is seen in polar covalent bond. This happens when there is electronegativity difference, but that electronegativity difference is not so significant. It's okay, it's mediocre. Okay, that is, electronegativity difference is there, but that electronegativity difference is not so high. Okay, it's just average. Okay, it is there, but it is average, it is medium. In such case, they go for polar covalent bond formation where they share their electron. However, that electron is not justly shared. It is shifted, the electron cloud or the pair is shifted towards the more electronegative atom. So that is polar covalent bond. It is different from our ionic bond, where ionic bond is formed between two atoms with significant electronegativity difference. That is to say that one atom will be high electropositive. It will be electropositive and the other atom will be electronegative. So you can say that the bond is formed between electropositive atom and a electronegative atom. Sufficiently electropositive and sufficiently electronegative atom, the bond is formed by. Now tell me, which is electropositive, sufficiently electropositive? Tell me that. Yes, metals are sufficiently electropositive. And which are sufficiently electronegative? Yes, non-metals are sufficiently electronegative. So this kind of bond is shown by metals with non-metals. Metals with non-metals, because metals are sufficiently electropositive. They are the highest electropositive. They are electropositive in nature. And non-metals are electronegative in nature. So it's shown by metals and non-metals, a bond between metals and non-metals. Now, tell me one thing. Where do metals exist in the periodic table? Where is their place? This is the periodic table. Okay. Now where do metal exist here? Yes, this side of the table, the metal exists. That is on the left side. Metal exists, and on the right side, barring this is the inert gas. Okay, barring this area, on the right side, non-metals exist. So you can say it is the bond, ionic bond is the bond formed between elements on the left side of the periodic table with elements on the right side of the periodic table. You can also say like that. Let us see some examples of such metals. Okay. Number one, elements that belong to group 1A. Group 1A. Okay. So look at Na plus sodium. It gets stable when it loses one electron. It achieves an inert configuration in the outermost shell when it loses one electron. So it is stable ion, sodium. What about lithium? Of course, that is also stable ion. So these atoms become stable when they lose one electron. They become stable when they have a charge of +1, and therefore these atoms get involved in ionic bond formation. Correct? Okay, they will form bond with the one who accepts their electron. Okay, so these atoms go for ionic bond formation. Let us see other examples of compounds. What about group 2A compounds? Look at this, magnesium and calcium. They lose 2 electrons. So when they lose 2 electrons, they achieve inert configuration. Correct? They achieve that octet configuration in the outermost shell. So they achieve stability, they achieve inert configuration when their charge is +2. So they get involved in ionic bond formation with those atoms which are ready to accept their 2 electrons that has been lost from them. Correct? Let us see third example, group 3A elements. Group 3A elements. Look at Al3 plus. Al3 plus. Now aluminum becomes, its atomic number is 13. Okay. So aluminum becomes stable. It becomes inert configuration when its charge is plus 3 or when it loses 3 electron. So therefore to that atom which has accepted its 3 electrons, that atoms makes ionic bond with aluminum. So such atoms are, they may go for ionic bond. They go for ionic bonds formation, correct? So they are on the left side of the table. They go for with what? With elements on the right side of the table, right? Now there are some complex ion also. I want to say here that there are some complex larger metal ions that also go for ionic bond formation. For example, Fe, iron. It can be stable in both forms. There can be more than one stable forms for iron, right? Ferrous and ferric. So such larger metal ions exist which are stable in more than one ionic form, right? Examples of this is tin, lead, and your other heavy metals like nickel. All this can show various ionic, they are stable in various ionic forms, okay? Now let us see those atoms, examples of those atoms which are capable of accepting electron. Group 7a elements, okay? Let us see the example: Cl minus, Br minus, I minus. Okay, they become stable when they accept one electron and their charge is -1. Okay, they become stable. So what they do, they take electron from those who are donating it. Okay, and after taking that electron, they become stable. Of course, they are stable ions. They become stable, of course. But what would happen? They would go for electrovalent bond formation, or therefore they will go for ionic bond formation. That is what happens. Other examples are group 6a elements. Group 6a elements. For example, O2 minus. Okay, they are having stability. They achieve stability, or they achieve inert gas configuration where when their charge is -2, or when they accept 2 electrons in their outermost shell. Okay, so okay, they are stable when they take these 2 electrons, but these atoms then become negative. Its neutrality goes, because now the number of protons is less than the number of electrons. So their neutrality goes, so therefore now they are negative. But then after becoming negative, of course they will go for electrovalent bond formation. Other examples are group 5a elements. 5a elements. For example, N3 minus, nitrogen. They become stable when they accept 3 electrons in their outermost shell. 3 electrons in their outermost shell. Okay, then they lose their neutrality after accepting 3 electrons. After losing their neutrality, of course they would become negative, and not -3, negative actually, and then they will go for ionic bond formation. So these are the examples of atoms that go for ionic bond formation. Dear students, I hope you have understood till now. Let us go to another concept which is called as crystal lattice structure of ionic bond. Crystal lattice structure. Okay, so when we are talking about one sodium and chlorine, okay, it is very obvious that it is not only one molecule that go for ionic bond formation at a single time. Simultaneously there are millions of molecules that will go for ionic bond formation. Millions of the same atoms, they will go for ionic bond formation. So when you are doing a reaction, it is very obvious that you are not taking only 2 atoms. You are taking 1 mole, or you are taking some quantity. So when you are taking Na plus and Cl minus, you are taking some quantity, correct? You are not taking only 2 atoms. So millions of compounds simultaneously they will go for your ionic bond formation, and that would lead to a formation of crystal. That will lead to a formation of crystal. Now the question that comes before us is, what is the arrangement of molecules in the crystal lattice structure? What is the arrangement of molecules in the crystal lattice structure? To answer this question, I want to tell you that there are two forces that are existing in this crystal lattice structure. One is the force of attraction. Attraction between what? Attraction between unlike charges. Correct? Unlike charges attract each other. And the second force is the force of repulsion. Repulsion between what? Repulsion between like charges. Correct? So there is in the crystal lattice there is Na plus Cl minus, both charges are there, positive and negative. Like charges will repel each other. For example, Na plus here will repel the Na plus here, right? Cl minus here will repel Cl minus here. Like charges will repel each other. Unlike charges will attract each other. Okay, if Na plus is here, then it is stable. Correct? They attract each other. Okay, so what happens is, in the arrangement of the crystal lattice, the negative ion is surrounded by positive ions. The negative ion is surrounded by the positive ion, or the negative end of one molecule is surrounded by the positive end of another molecule. Correct? The arrangement is such that the negative end of one molecule is surrounded by the positive end of the other molecule, and vice versa. Here what would happen? The negative ion will surround the positive ion. Okay, arrangement is such that the negative ion, this is the positive, now this will be surrounded by negative. Correct? So the arrangement is such that the negative ion is surrounded by positive ions of the molecule, or the negative center of negative end of one molecule is surrounded by the positive end of other molecules. Arrangement is such that the positive end of one molecule is surrounded by the negative ends of other molecule. Correct? So the arrangement is in alternate fashion in the crystal lattice structure. Crystal lattice structure, the arrangement is in alternate fraction. Therefore, the net charge of the crystal lattice is how much? 0. If you take a single point, if you cut a piece from here, will there be any charge? No. Correct? Because everything becomes neutral. Correct? They are of course held by strong electrostatic force of attraction. It's very difficult to break the crystal lattice. They are of course held by the strong electrostatic force of attraction, but if you take a section, or if you take a one point, or if you take the crystal lattice as a whole, the net charge is nothing but 0. Yes, charges exist, but the net charge is actually 0. So that is the crystal lattice structure of ionic compound. We have seen that the crystal lattice structure is very strong. Why they are strong? Because it is held by opposite forces of attraction. It is held by electrostatic forces of attraction. The ionic bond is a very strong bond. It is the strongest bond. It is more strong than the covalent bond. They are held tightly. Correct? They are surrounded. Correct? So we have seen that. Fine. Now, in the formation of such ionic, if two atoms they are combining to form ionic bond, there will be energy that is released. Correct? That energy is small. We cannot measure it. Okay? We are not able to measure it. But when millions of atoms combine and they form molecule of NaCl and they form a crystal lattice like this, a measurable amount of energy is released. That measurable amount of energy is called as the lattice energy. That is called as lattice energy. So lattice energy gives you an estimate of the strength of ionic bond. Am I right? Just think about it. Yes, we know that if two atoms combine, they form a molecule. Yes, some energy is released. We are not able to measure that energy because that's so small, right? But when millions of atoms combine and they form a big lattice structure, they form a crystal lattice structure, a measurable amount of energy is released, and that energy is called as the lattice energy. So therefore, lattice energy gives you an estimate. It doesn't give you complete accurately, but it gives you an estimate of the strength of ionic bonding. right? Greater the lattice energy, that is greater the energy released, that is greater the lattice energy, greater will be the strength of the ionic bond. Greater will be the strength of the ionic bond. So what to do if you want to know the strength of ionic bond accurately? Is there any method? Yes, there is a method. This law is called as the Coulomb's law. You might have heard it. Coulomb's law of attraction. Coulomb's law of attraction. Okay, so what happens is here is that we are saying that the force of attraction is proportional to your charges. Correct? The force is proportional to charges and the force is inversely proportional to interatomic radius. So you can combine 1 and 2, you get force is directly proportional to charges and inversely proportional to interatomic radius, right? So that is the Coulomb's force to know the ionic strength. Now you want to remove this proportionality sign, correct, to calculate, correct? There should be some measurement here. So that is force is K, which is constant, Q1 Q2 divided by R. The value of K is 6.85 into 10 raised to the power 9 Newton meter square per Coulomb square. K represents the force of attraction when unit charges are separated by unit distance. When unit charges are separated by unit distance. Dear students, what I am saying here is that lattice energy does not just gives you an idea of the strength of ionic bond. It doesn't give you accurately. To know accurate ionic strength, you need to go for Coulomb's law, Coulomb's force. So Coulomb's force, that is the strength of an ionic bond, is directly proportional to the charges and it is inversely proportional to radius. Okay, if greater the radius, if greater the interatomic distance, then longer will be the bond, then lesser will be the ionic bond energy. Correct? It's obvious. If greater the charges, then greater the ionic energy, ionic bond energy. So we have given you like this proportionality sign. Correct? Now we have to remove this proportionality sign. There should be some constant value here. Okay, this can differ, but there should be some value which is fixed. Okay, minimum value. So that minimum value is 6.85 into 10 raised to the power 9 Newton meter square per Coulomb square. Okay, that minimum value is what it represents. It represents the charge. It represents the force of attraction when unit charges are separated by unit distance. I hope you have understood this. So that gives you that tells you accurately the strength of ionic bond, the strength of ionic bond. Now let us see the properties of ionic bond, the properties of ionic covalent compounds. Now Na plus Cl minus, it exists as this, right? First of all, I want to say that if you dissolve it in water, what will be the situation? It would exist as ion. Okay, therefore in aqueous solution they are good conductors of electricity. They are good conductors of electricity. Okay, no water. If they are in molten state, then also they will exist as ions, and then also they are good conductors of electricity. So in aqueous solution and in molten state, ionic compounds are good conductors of electricity. Okay, what is the second thing? NaCl, right? The crystal lattice of NaCl is very hard, right? It is very strong force of attraction, correct? So it is very hard to break them. It is very strong. That means that the melting point and the boiling point of ionic compounds are very high. Melting point and boiling, because it is very hard to break the intermolecular force of attraction. It is very hard to break the strong electrovalent force of attraction between them. So the melting point and boiling point, of course, of ionic compound will be very very high. The third thing is that they are polar, correct? They are polar. They participate in reaction very rapidly. Because they are polar, they can break easily, they can participate in reaction very rapidly. Okay, anything positive can come and attach here, anything negative can come and attach here. So they react rapidly, correct? They react rapidly, especially in aqueous solution they will react very very rapidly, correct? So these are the points, or these are the properties of ionic compounds. Dear students, we have seen that ionic compounds, it involves ion pairs, yes, it involves positive atom and a negative atom, but as a molecule, when they combine with each other, they are neutral. Because when positive combines with negative, the molecule in itself becomes neutral. We have seen firstly why they do so to attain inert gas configuration. All that we have seen, and we have seen the crystal lattice structure, and finally we have seen the properties of ionic compounds. Dear students, I hope you have understood the class. If you have done so, if you have found the class useful, please do not forget to subscribe this channel. Like it and do share it with your friends. Thank you very much.